Hello, and welcome to the next recording session on, actually I'll be talking and introducing a bit about correlation analysis and regression. Okay, to begin this, let's go back and review, we've talked about variance of a single variable, and what variance measured was a sense of variability or spread of your population with respect to a single random variable. A covariance of two random variables, x and y, with a probability density function of p of x of y, is given by the first formula as you see. Intuitively, you can see that it's similar to what we were looking at with a variance of a single variable. But we are now looking at pairwise comparisons or values of x and y. And you see it's very similar to what we had before. We're just doing a dual sum over x and y, all possible values of x and y for the two different random variables times the joint probability p of x, y. And if the values are discrete, then it's a summation. And of course, if they are two continuous random variables, then you are, just as you did with the single variance of a single continuous random variable, you did an integration. And what we're doing now is looking at the covariance. Okay, so with this covariance, we turn our attention to something called the correlation coefficient. So here is what we're working with. We have two random variables, x and y, with a covariance, sigma xy, and standard deviations, sigma x, sigma y, respectively. Then the correlation coefficient of x and y is given by, and typically it's written with this row of subscript xy, and it's the covariance divided by the product of the standard deviation of x and the standard deviation of y. Statistical analysis, so correlation analysis, what is it? It's used to obtain a quantitative measure of the strength of a relationship between a dependent variable and one or more independent variables. The strength of a relationship. And one of the things that happens is that, just as we've been doing, so did we know the population mean? Did we know the true population standard deviation? We've been through a number of different topics related to this and drawing samples, using a sample mean as an estimate for a population mean, using a sample standard deviation as an estimate for the population standard deviation. We throughout the textbook, and I've introduced a bit of it in class, we've talked briefly about the difference between two means, a lot of sampling and using those sample results as estimate for the population. So we do the same thing here. We draw a sample, and the sample values we are going to use, and here's this nice, beautiful formula. We can use those sample values to create an estimate for the true correlation coefficient between two random variables. And so this is a formula for what you would do with a sample of size n. The value of r, or rho hat, however you denote it, certainly would fall between -1 and 1. And something called the coefficient of determination is r squared times 100%. And what kind of relationships could you have between x and y? And this is just showing if you map them out, y along the vertical axis, x along the other. You see in the upper left, direct linear, which means every time x increases in a linear relationship, y is increasing. Relationship inverse linear, so they're following the linear function but going downward. So as x decreases, y is let's see, as x is increasing, y is decreasing. You see the direct curvilinear, so, some sort of nonlinear functions, and you have direct ones, inverse linear with more scattering, so how tight is that relationship? That's the middle one on the bottom, shows a difference. You can see it between the one right above it. There's less scattering in the one above, a little bit tighter relationship presumed. Linear relationship. No relationship, can't really map a function to that. And so for correlation, with this, there's a relationship between two random variables. What's the strength of the relationship is a question to be asked. And what is the form of the relationship, just as I looked at a minute ago? Inverse, direct, linear, nonlinear. If it's nonlinear, what type of nonlinear function? But we might start off simple and say, okay, you know what? What about the linear relationship? Can we do a quick test to see if there's a linear relationship or not? And we're going to look at this T statistic. So to test for no linear association between X and Y, you calculate this. R again is calculated from your sample that you've drawn. So R times the square root of n minus 2 divided by 1 minus R squared, where R is the sample correlation coefficient that calculated a couple slides back with that formula, and n is the sample size that's drawn. And you could conclude, and this is just as we've been doing with our confidence interval, the two-sided hypothesis testing, got an alpha over 2. We conclude with no linear association if your T value that you calculated from your sample falls within a minus T alpha over 2 with n minus 2 degrees of freedom on the negative and the positive on either side of your T statistic that you've derived from your sample. So otherwise conclude that there is a linear association between X and Y and proceed with a regression, something called a regression analysis, which I'll look at next. So this is just a simple, quick test. You draw your sample, you calculate an R value from that sample, which is an estimate for the true correlation coefficient, rho. You take a look and see if the sample T value that you've calculated using that sample correlation coefficient estimate falls in the range of T alpha over 2 with n minus 2 degrees of freedom. If it falls in the range, then you could conclude that there's not a linear relationship. If it falls outside of that range, then you go ahead with your regression. Okay, so the data used for illustration. So here's an example. Okay, so data used for illustration are from a study of two methods of estimating tread wear of commercial tires. The data shown here are shown here and plotted. The variable which is taken as the independent variable X is the estimated tread life in hundreds of miles by weight loss method. The associated variable Y is the estimated tread life by groove depth method. So weight loss versus groove depth method. Okay, so this is hard to see, but again, if you have a hard time seeing it, pull it up in the Blackboard. You'll see the original PowerPoints off of this. But here we have pairings of values of X and Y drawn from a sample. And you can plot these, and you see that, and you just quickly eyeballing it, you see that there's some sort of direct relationship to them. So from those numbers, you can calculate, and go back to that R, and the formula for using sample data to calculate an estimate for your correlation coefficient. And this one turns out to be an R of 0.948. Calculating a T with that, 0.948 times the square root of 16 with the sample size, minus 2 divided by 1 but divided by the square root of 1 minus the 0.948